In this lesson, we're going to talk about basis for a vector space, but not just any basis. We're going to talk about a very special type of basis called an orthonormal basis. So what is an orthonormal basis? An orthonormal basis is a basis that has the following two properties. First of all, every single element in the basis has a length or a magnitude of 1 unit. This is where the portion of the word normal is coming from. When we talk about a vector being normalized, that means that that vector has been rescaled to have a length of 1. So the second half of this word, normal, refers to the fact that every element in the basis has been normalized and has a length of exactly 1 unit. The second property of this orthonormal basis is that every single element in the basis has to be orthogonal to, at a right angle to, perpendicular to every other element in the basis. So that's where the first half of this word is coming from, ortho. Ortho being related to orthogonal, orthogonal referring to perpendicular. We are familiar with orthonormal bases, even though this might be our first encounter with this particular piece of terminology. For example, these vectors I hat, j hat, and k hat that you encountered in Calc 3 and maybe in physics, these vectors form an orthonormal basis for R3. Now, when you're trying to determine whether a set of vectors forms an orthonormal basis, there are effectively 4 qualities that needs to be checked. The first 2 qualities are just a part of asking the question, do you have a basis at all? And to see if you have a basis at all, you need to check 2 things. Are the elements in the set independent? And then do the elements in the set span, in our case, R3? Then you need to check the actual orthonormal part of this definition. You need to check 2 more properties. Do all the elements have length 1? And are all the elements perpendicular to each other? So let's think about whether these 4 qualities are possessed by this set of vectors. We've got I hat being equal to 1, 0, 0. We've got j hat being equal to 0, 1, 0. And we've got k hat being equal to 0, 0, 1. I can see at a glance that these vectors are independent because there's no way to obtain any of these vectors by combining the others. So they're independent for sure. 2, do these vectors span R3? Yes. Every single vector in R3 can be constructed as a combination of I hat, j hat, and k hat. That is the foundation for the physics notation for 3-dimensional vectors. Do all of these vectors have a length of 1? Yes. Once again, I can see that at a glance. The vector I is 1 unit long in the x direction, the vector j is 1 unit long in the y direction, and the vector k is 1 unit long in the z direction. So that property is also satisfied. And then there's a question of, are they all perpendicular to each other? Do they all stand at right angles? And again, for vectors this simple, that can be seen at a glance. The vector I points in the x direction, the vector j points in the y direction, the vector k points in the z direction. So all of these vectors sit at right angles to each other. So with that, we have verified not only is this set a basis for R3, but also this set is an orthonormal basis for R3. All the vectors have a length of 1, and they are perpendicular to each other. Another orthonormal basis that you've encountered before now is in Calculus 3. In Calculus 3, when you had a vector-valued function r of t, you calculated what were called the unit normal vectors and the unit tangent vectors for curves like that. So the unit tangent vector was this vector capital T, And the unit normal vector was this vector capital N. And these vectors were characterized by two main properties. Both of them had been rescaled to have a length of 1. That was part of the definition and the formula in Calc 3 that you learned for these vectors. And also, perhaps in Calc 3, you learned that T and N are constructed to be perpendicular to each other. Now that we've talked about what an orthonormal basis is, I want to talk about why orthonormal bases are amazing, why you always want an orthonormal basis if you can get it. So to talk about why orthonormal bases are amazing, let's go back to talking about regular bases for a moment, and let's talk about a weakness or a limitation of a regular basis for a vector space. When you have a regular ordinary basis for a vector space, you know by definition that every element in the set can be expressed as a linear combination of these elements. Because the vector space is spanned by these elements, every single vector in the space can be understood as a linear combination of these elements. However, sometimes you might want to know what specific values of C1, C2 through Cn are required to generate a specific vector W. For example, we encountered a situation like this back in our lesson on column space as a span. What we wanted to do was find these specific values of C1 and C2 needed to construct W as a combination of these two vectors. To do that, we expressed this problem in the language of an augmented matrix. And then we had to row reduce that matrix, and we had to interpret these solutions to that row reduced matrix. And the solutions to that row reduced matrix gave us the coefficients on V1 and V2, the specific coefficients needed to produce this specific vector W. So in general, if you're trying to find the specific coefficients needed to generate some specific output, you need to do row reduction in order to make that happen. That's usually how this process goes. So this was not an awful process, but if you have an orthonormal basis, finding these specific coefficients becomes much faster and much easier. Let's go ahead and see that in action. So in this problem, we have two vectors u1 and u2. And these two vectors form an orthonormal basis for R2. And to confirm that, we can, for example, go in and check the lengths of these two vectors. If I look at the magnitude of u1, the magnitude would be found by taking the first entry squared and the second entry squared, which would become under the root 4 plus 1 over 5. So that's 1 for sure. And the same thing is true for the length of u2. If I check that, I get negative 1 over root 5 squared, 2 over root 5 squared. And so that's also going to become 4 plus 1 over 5, which becomes 1. So the normal part of orthonormal is satisfied. All of the vectors in this set have length of 1. Let's also check that they are perpendicular to each other. And if you want to see if two vectors are perpendicular, you can just calculate their dot product, right? And see if the result is 0. So the dot product of these two vectors would be 2 over root 5 times negative 1 over root 5 1 over root 5 times positive 2 over root 5. And if we add those together, it cancels out. So the dot product between the vectors is 0, and that proves the orthogonal part of these guys being an orthonormal basis. When we have an orthonormal basis, let's see how easy it can be to take a specific output vector and find the coefficients that are needed to generate this vector. Let's find a specific combination of C1 U1 plus C2 U2 that generates the specific output vector W. What I'm going to do to help me to calculate that result is I'm going to go into this expression and I'm going to dot both sides of the equation with the vector u1. Dot both sides of the equation with the vector u1, and we get c1 times u1 dot u1 plus c2 times u1 dot u2. And that's going to be equal to u1 dot w on the right. Now notice that because u1 and u2 are orthogonal, then u1 dot u2 vanishes and becomes 0. As we noted earlier, because the two vectors are perpendicular, their dot product is equal to 0. Additionally, u1 dot u1 simplifies in a really nice way as well, because when you dot a vector by itself, the result of that is equal to the length of the vector squared. Because the vector has a length of 1, u1 dot u1 becomes 1 squared. If I clean up this expression, what happens? On the left-hand side of the equation, I get the number c1. C1 is equal to U1 dot W. So notice what this equation now is saying is that if you want to calculate C1, you do not have to do this whole lengthy row reduction process to find that value. If you're lucky enough to have an orthonormal basis, you can find the value of C1 just by dotting the first basis vector with the vector that you're trying to produce. Similarly, you can find the other coefficient, you can find the other C2 just by dotting the vector U2 with the vector that you're trying to produce. The second coefficient can be found just by dotting U2 with your W. So if someone asks me to express the vector W as a combination of these two vectors, all I have to do is find the coefficients using these two simple dot products. C1 being U1 dot W would be this vector 2 root 5, 1 root 5, dotted with the vector 4 comma minus 1. And if you calculate that dot product, you get 8 over root 5 minus 1 over root 5, result 7 over root 5. C2 would be U2 dotted with W, negative 1 over root 5, 2 over root 5, dotted with 4 comma minus 1. So that would be negative 4 over root 5 minus 2 over root 5. Result, negative 6 over root 5. And with that, we've gotten the two coefficients that we need to build W as a linear combination of these basis vectors. The first C1 applied to that first basis vector, and then combine that with C2, negative 6 over root 5, times the second basis vector, negative 1 over root 5, 2 over root 5. And that combination would produce the vector W given to me in this problem. So this is the major advantage of orthonormal bases. If you have an orthonormal basis, finding the coefficients needed to produce any specific output value becomes very, very easy because you can get them just as a dot product calculation. So to summarize that, if you have an orthonormal basis for a set, then for any W in that set, for any W in that vector space, W can be expressed as W dotted with U1 applied to U1 plus W dotted with U2 applied to U2, and so on and so forth, the final coefficient being W dotted with UN, applied to UN. You can find these coefficients easily just using dot product. Once again, although this might seem like a fresh concept, you might have encountered this idea already as you dealt with unit tangent vector and unit normal vector in Calculus 3 and possibly in dynamics. In Calculus 3 and in dynamics, if you had the acceleration for a moving object, you took that acceleration vector and you split it into two parts. One part which was aligned with the tangent vector t, and one part which was aligned with the normal vector n. So in other words, you took your acceleration vector and you expressed it as a linear combination of t and n. But because t and n form an orthonormal basis, because both the vectors were unit vectors, and because they were perpendicular to each other, you could find these components of acceleration, you could find these coefficients very easily just using a dot product. The tangential component of acceleration was a dot t, and the normal component of acceleration was a dot n. So that concludes today's lesson. Today we talked about what's called an orthonormal basis for a vector space. An orthonormal basis is a basis that satisfies two additional special properties. First of all, every element in the basis has to have a length slash a magnitude of 1 unit. And second of all, every element in the orthonormal basis has to be perpendicular to every other element within that basis. And the standard basis vectors I hat, j hat, k hat are a quintessential example of an orthonormal basis. The reason why orthonormal bases are so wonderful is that it makes it very easy to write down any vector as a combination of your basis vectors. Under normal circumstances, if you want to write down a vector as a combination of your basis vectors, you have to do row reduction in order to find the values of the coefficients. But if your basis happens to be orthonormal, finding those coefficients is much easier and it doesn't require any row reduction. If your basis is orthonormal, then you can just find the coefficients using a dot product.